Hey, welcome to The Explainer. Today, we're going to tell a story. It's about one of machine learning's most intuitive algorithms, and we're going to do it by following a single lost data point on its quest to figure out where it belongs. Through its journey, we're going to uncover the simple but really powerful idea behind k-nearest neighbors. So let's just kick things off with a simple question. Think about it. When you run into something totally new, maybe a movie you've never heard of, a song that just pops up, how do you figure out what it is, or if you're even gonna like it? You probably compare it to things you already know, right? And believe it or not, that's the exact same problem our main character is facing today. A single, unclassified data point just floating in a sea of information trying to find its place. So here's our hero. We're gonna call it XQ. And as you can see, XQ is totally lost, surrounded by all these other points that already have a label. They're either a plus or a minus. And our hero is asking just one simple question. Who am I? Am I a plus or am I a minus? So how in the world can our little data point figure this out? Well, the solution to its identity crisis actually comes from a super old, very wise saying. That's it. That's the whole idea in a nutshell. We can figure out what our point is just by looking at its neighborhood, by looking at the company it keeps. If it's surrounded by a bunch of pluses, chances are it's a plus. If it's hanging out with minuses, well, you get the picture. Now, this really simple idea belongs to a category of algorithms called instance-based learning. They're also known as lazy learning, which is a great name because it's so accurate. See, these algorithms don't do all the hard work up front to build some big, complex model. Nope. They just store all the examples they're given and kind of chill out, waiting until the very last second when a new point like our XQ shows up.
Okay, but that brings up a really important question, right? When we're talking about a bunch of dots on a graph, what does neighbor even mean? How do we define close?
It's all about distance. How close are you? And the standard way we measure this is with something called Euclidean distance. Now, don't let the fancy name scare you. It's just the straight line distance you learned about back in geometry class. We're literally taking out a ruler and figuring out who is closest to our hero, XQ. Now, this is where it gets really fun. Our point knows how to find its neighbors. So what's next? Well, it does what any good community would do. It takes a vote. This whole process is called the k-nearest neighbor algorithm, or KNN for short, and it's basically just 4 simple steps. First, you pick a number, k. That's how many neighbors you're going to ask for their opinion. Step 2, you find those k closest points. Third, you let them all vote. And finally, majority rules. Our point gets assigned to whatever class got the most votes. Simple as that. Okay, let's actually see how this plays out. And you'll see pretty quickly that your choice for k, that number of neighbors, is a really big deal. We could pick k equals 1, where our point only asks its single closest friend. Or we could go with k equals 5, where it pulls a wider group of 5 neighbors. And as you can probably guess, that choice can totally change the result. And check this out. This is where it gets wild. When k is 1, the single closest neighbor is a plus. So the vote is 1 to 0, and our hero gets classified as a plus. But when we set k to 5, we look at that bigger group. And all of a sudden, we've got 3 minuses and only 2 pluses voting. The majority flips, and now our point gets classified as a minus. The outcome completely changes. So what's the big takeaway here? Choosing k isn't just some small detail. It's a huge decision. In machine learning, we call this a hyperparameter. It's like a knob that you, the person building the model, have to set just right before anything else happens. And as we just saw, that one number can totally change the ending of our story.
Okay, so our little story seems pretty straightforward. But in the real world, things are never that simple, are they? There are a couple of catches, a couple of plot twists in our hero's journey that we need to talk about.
One common twist is that we can weigh the votes. I mean, think about it. It just makes sense, right? A neighbor that's right next door should probably have a bigger say than a neighbor who lives 5 blocks away. So we can actually do that by giving more weight to the votes of the closer neighbors, basically making their voices louder in the election. But KNN has this one giant weakness, a sort of Achilles heel. It's a famous problem called the curse of dimensionality. Let me try to explain. Imagine you have points just on a single line. Finding the closest neighbor is super easy. Now imagine them on a flat sheet of paper. A little harder, but doable. Okay, now imagine a space with 100 different dimensions. Suddenly, everything is so far away from everything else that the very idea of a close neighbor starts to break down and lose its meaning. And that can really hurt an algorithm that's all about distance. All right, so we followed our little hero XQ on its big journey to find an identity. What's the point of all this? Why does this simple story actually matter in the big world of machine learning? Let's do a quick pros and cons list. On the pros side, KNN is incredibly simple to get your head around. It's a lazy learner, so you don't have a big, complicated training step, and it can actually handle noisy data pretty well. On the con side, though, it can be really slow when it's time to classify because it has to compare the new point to every single point it's ever seen. It's also really sensitive to features that don't matter, and of course, it suffers from that pesky curse of dimensionality we just talked about. At the end of the day, the story of KNN is so great because it teaches a really core lesson in machine learning. You can learn a lot just by measuring how similar things are. This whole idea that you can understand something new just by looking at what's known and nearby, that's a cornerstone of the entire field. It just goes to show you that sometimes the simplest ideas are the most powerful. And that leaves us with one last big question to chew on. Our hero found its place by measuring a simple, straight line. Easy enough. But what happens when closeness isn't that simple? I mean, how do you measure the distance between two sentences, or two photographs, or two pieces of music? Answering that question, well, that's where the next chapter of the machine learning story really begins.